All right, so now we're going to say a little bit about algorithmically how do you address the question of determining whether things are connected. And this is going to fall, it's like into the framework of what are called disjoint set systems. Uh, okay, and so in particular, we're going to look at the graph case. So returning to graphs. Right. So I want to describe again an algorithmic way of determining whether a graph is connected. Okay. Okay. So and the way we're going to do this is to consider an approach which is based on maintaining a disjoint set system. Right. So I'm going to consider, and there are of course many ways of doing this. So I'm just describing one possibility. All right. So again, it's like we're in the setting of graphs. So we're going to label the vertices from 1 to n. So I label the vertices from 1 to n. Okay, and then you can think of the components as being subsets, of course, of this set of numbers from 1 to n, right? And then we store components as subsets of this big set, which I denote by n square brackets, which is just a set of integers from 1 to n. Okay, and so the idea first is to assume that everything is disconnected. All right, so you have again these n vertices. You assume each of these things are all disconnected from each other, and then you go through the edge list, and then every time it's like there's an edge, it's like connecting two sets which you had assumed to be disconnected, you would connect them, or you would take the union. Okay, so that's the basic idea. And then once, of course, you've gone through the entire edge set, if the only set of connected components you have, it's like if that set only has one element, then you know that the graph actually is connected. Otherwise, of course, it's disconnected. And of course, the remaining it's like connected components, it's like what you get, it's like from this set would give you a separation, it's like of the graph as well. Okay, so you start with n disjoint components, one for each vertex. And then you merge components that are connected by an edge. Okay, so after you've done this for all the edges, so if after doing this for all the edges, right, you are just left with one component, then the graph obviously is connected. All right, so that's sort of the high-level picture of what's going to happen, and we're going to build this algorithm. It's like on two basic operations. So let's discuss that. Okay, and then once we talk about those basic operations, I will also describe the data structure. It's like one would use, to represent that set of disjoint components. Okay, so we need sort of two basic operations. Okay, so the first one is the find operation. Okay, so find I. Okay, what this does is that it returns the name of the set containing vertex I. Okay, and then there's a union of I and j, and of course what you expect is that this will combine, it's like the components, it's like which I is in and the component which j is in. Okay, so if I and j belong to different sets, right, you replace the two sets with their union. Okay. All right. Okay. So of course it's like you use find to test if I and j are in the same set. And then you use union if they belong to different sets. Obviously assuming if you have an edge, it's like I comma j, right? So, all right, so you might ask, well, how should I represent this as a data structure, right? So you know that you have n vertices, so it's natural to consider first an array, it's like of n entries, okay? All right, so let's just start with a simple problem. Let's say 5 vertices. So 1, 2, 3, 4, 5. All right, and then I'm going to represent the sets, if you will, as a graph. Sorry, as trees, as a collection of trees. Okay, so as an example, if 5 was connected to 3, was connected to 2, and connected to 1, right? So I have a connected component with 4 elements, and then another sort of lone component. It's like with just the element 4, the 4th vertex. So what I'm going to do is that I'm going to look at this array, and then associated with each entry, I'm going to have essentially a pointer or an arrow to the parent of the element here. So 1 has a parent, which is 3. So 1 points to 3. So I imagine having a pointer which goes to 3, right? And then 3 has a parent, which is 5. So there's a pointer from 3 to 5, right? 2 has a parent, which is 5. There's a pointer from 2 to 5. Okay? And then 5, it's like doesn't have a parent. It's the root of the tree. Okay? And then 4 doesn't have a pointer going out. It's the root of its own tree. Okay? So one way to sort of label these sets then is to basically say that, well, if you have an element which is in this set, then you label it by the root of that tree. All right, so the two disjoint sets are labeled 4 and labeled 5, and the basic idea then is that if you were trying to figure out what is the set associated with 1, you just traverse this, it's like tree backwards to the root, right? So 1 points to 3, which points to 5. So you label, it's like the vertex 1 with set number 5, okay? So that's more or less what's going to happen with the find routine, is that it's going to, look at the entry, it's like for I, and then sort of follow the parent links backwards until you end up with an element which doesn't have a parent, and then it outputs that label for the vertex. Okay, so again, it's like the roots are going to be how you label the different sets. Okay, so again, the relevant data structure is a tree represented as a linear array with a pointer to the parent. Okay, so the relevant data structure is a tree, right? But sort of represented or implemented using a linear array with sort of pointers to the parent sort of vertex. Okay. All right. So if you, with that in mind, let's see what happens. Okay. So I can write down a little bit more explicitly what the pseudocode for this is, right? So I could have, it's like find I, which returns an integer. It's like as the label, okay? And if you recall again, the label is going to turn out to be the root of the tree which it's in, okay? So if the vertex, the ith vertex, right, parent is null, is not null, right? So that means it's not the root of a tree, okay? Then you return the find of that parent, okay? So if this is not a root, then you apply the find routine, it's like to the parent, okay? So you're sort of doing recursion here, okay? So let's see, let me sort of use these square brackets. Find vi dot parent. Okay. Else, if it is, it's like a root, right? Return just the label. Return I. Okay. So, all right. So, for example, it's like if you want to find 1, right? You look at 1. It's it has a non-trivial parent. It's like pointer. So I will output instead the value of find 3, right, which is the parent of 1, okay? And 3 again is not a root, okay? So I will return the value of find 5, okay? 5 is a root, so I'll just return 5, okay? So the point is that if you're at 1, 2, 3, or 5, it's like when you apply the find routine, you will return the number 5. And if you were 4, you return the number 4. Okay, so that gives you a way of systematically labeling the disjoint sets. It's like in a way which doesn't take too much effort. Okay, so so that's saying that the components are labeled with the root of the tree, okay, which is kind of a nice way of doing things. Then you can construct the union operation. Okay, so this doesn't return anything; it just sort of changes the links in some sense. Okay, so if you want to take the union of the two sets associated with a point with elements or vertices I and j, then what you have to do is you first have to find the sets they belong to, right? So you let x be find I, and y be fine j. Okay. And then you have to check whether or not it's like they actually belong to disjoint sets. So if I is not equal to j, so they actually disjoint, then I want to say I now want to link these two things together, right? This set with this set, okay? Then I can keep the root of one of them and then sort of add a link from the root of the other one to the root of the first one, right? So that's more or less what you need to do. So if sorry, that's not what I'm saying. If x is not equal to j, x is not equal to y, right? So these are two different sets, right? X and y are the labels of the set, right? Then I can let the parent, so vx dot parent, which was originally null, right? Because both of these things, x and y, are by definition roots. Okay, so they have null parents. Okay, so I'm going to redefine the parent of one to be the root of the other y. Okay, so for example, in this case, it's like what I could have done is to, you know, put 4 down here and then make that, you know, 4 have 5 as a parent, right? So that would sort of involve putting a pointer from 4 to 5 like this. Okay, so that's a very simple way to connect everything that way. Okay, and then you end the if statement. Okay. All right. One thing, of course, you could do is that, so here, you know, I've made a arbitrary choice about which set I'm going to graft into the root of the other, right? So if you wanted things to be more efficient, in particular, the find operation depends on the depth of the tree. If you want the method to be faster, then it behooves you to try to minimize the layer depth, if you will, of the tree. Okay, so one way to do this is to always graft the smaller tree to the root of the bigger tree. Okay, and so you have to, you know, in your data representation, you have to include something about the height of the tree as well, if you want to be able to do that. I'm not going to sort of say too much about the details, but I'll just say that, so to improve runtime, right, we can instead graft the shorter tree to the taller tree. Okay, so again, it's like that requires you to know something about the height of the tree. It's like which you typically would just want to store. It's like as an internal variable. Okay, all right. So and there are of course other optimizations. It's like to these things you can do. So there are other possible optimizations which can be performed. But I'm not going to discuss them in too much detail. Okay. So anyway, so this gives you sort of the basic idea. It's like of you know, some of the algorithmic pieces. It's like which go into the question of, given a graph, how do you check whether or not it's connected, right? And as is often the case, it's like with algorithms, choosing the right data structure dramatically improves it's like the ease by which the algorithm can be implemented and the speed as well. Okay, so so that's it for today. It's like, and then we'll talk more about you know, sort of other aspects later on. Okay.